Well, this is working. This microphone working? Okay. There's always trouble with the on-off switch. You know, I find it hard to actually comprehend the situation that the introduction now takes so long. It feels like, oh, my career must be over if it takes so long to explain what I've already done. But coming back to something more close to home, this is home for me for a long time, for 4 years. And as I walk around the campus and I see what's going on now, I'm just so tickled to see the new labs and the bright people that are trying to make things happen in those labs. And who knows what's going to come next. I think about my career in a very chaotic process that led to where I am. And no one could have imagined it or predicted it. Certainly not in advance. It's even hard to explain afterwards. So anyway, I want to now tell you a story about the whole universe, from the Big Bang until the far future. And I cannot tell you every detail about that, but a little bit. So as was mentioned, I started off my childhood in a place in far northern New Jersey. And this actually is the research laboratory and bull barn. There were 20 bulls that lived in that barn, and there were also chemical labs and balances and all kinds of amazing things, and Geiger counters and cryogenic facilities in that barn. And it's no longer being used as a research station, but this was Rutgers University, and my dad was indeed studying dairy cattle breeding and feeding. So I got the idea that science was interesting, but to tell you the truth, I was a little intimidated by cows, and they were a lot bigger than I was, and I didn't want to pursue that subject. So anyway, but the sky was indeed dark at night, and I got to start. Now, I want to tell you what astronomers are up to, because we'd like to tell you as many pieces of this story of how we got here as we could. We have a story, which I'll tell you more about, from the Big Bang. We have pictures of it. We have stories about how the first galaxies of stars might exist, how they would come to change with time because they weren't born like they are, how stars are being made inside them even now, and planets around them, and how we would even have the conditions that would make it possible to have a concrete dinosaur on the Mall in Washington, D.C. So we can tell you a lot of the steps here, and then we have to talk to the genetic engineers and the biologists and the archaeologists to say, well, what are the rest of the steps about how come we have a college here in Swarthmore, Pennsylvania? But now I want to startle you something. When you look in the mirror in the morning, you are already looking inside of a star. Even if you're an astronomer, it is hard to comprehend this fact, but honest to goodness, that's the agreement of all the astronomers. The atoms that you are made of, the carbon, the oxygen, and the nitrogen, and the iron, and the sulfur, and everything that's in there, except the hydrogen, none of those were there in the Big Bang. They were all formed later by nuclear reactions inside stars. Stars blow up, the stuff goes back out into space, it is recycled, and here we are. We are recycled stars. And, just think, how could that possibly be? Well, it's not even after you study it for a long time, you don't quite believe it, but you know it's true anyway. So now I want to show you how we found out some of it. The first thing is astronomers really do look back in time. If you're a geologist, you look back in time by looking at old rocks, and you can find out sort of how old they are. And you see them in layers, and you dig them up, and you go deeper and deeper into time. Astronomers look back in time by looking at things that are far away. And light travels very fast, but it's not so fast that it doesn't matter. So you see the sun as it was 500 seconds before you look, because it took that long for the light to get here. The nearest star 4 years before it, you see it as it was 4 years ago. The middle of our galaxy is 25,000 light years away, so you see it as it was 25,000 years ago. And the Big Bang, approximately 15 billion. Now the new number is 13.7 billion years. That's how far back you can see in time. By the way, when we published one of our Kobe pictures, there was the Weekly World News, which you might see. I think they went out of print. But they showed a picture of our own galaxy, and they sketched in the pillars of heaven across the front. And they announced that we have to build a spaceship to go there. But anyway, coming back to more serious matters, how did we find out how big is the universe? Well, we have two basic methods. One is to draw triangles, as you would learn in elementary or high school, trigonometry. If you know one of the sides of a triangle and you know the angles of the triangle, you can figure out the other two sides. And so we've been surveying the sky this way for many centuries. In fact, the Greeks knew how to do this, and they got the size of the Earth about right by doing this. And some of them had actually gotten the distance to the moon about right by doing this. When that doesn't work anymore, you have to determine distances by comparing the brightnesses of things that are probably about the same. So if you know that this candle is the same brightness as this candle, then this is the basic formula for what's the relative distances. The intensity of the light goes down as the inverse square of the distance, so you can now build a yardstick to cross the universe by doing this. And it's pretty hard, but it's possible. And so we have measurements of distant objects this way. Now the other thing you want to know is how fast are things moving? Well, most things that move across the sky move so slowly that you can't tell. And even if you wait a long time, you can't tell, except for the planets, the moon, the sun, a few asteroids, and a few stars that are close enough so you can notice. The rest of them, what we can do is to tell if they're going towards us or away from us, because it changes the wavelength of light that we get from them. This is called the Doppler shift. So if it's coming toward us, the light gets bluer than it was. If it's going away from us, it gets redder. And so this is something that's been known for a long time. In fact, the fact that galaxies are going away was known in 1912, but it wasn't known what that was about. In 1912, we didn't even know what a galaxy was. Now we know it's a cloud of stars. But at any rate, this is tool number 2. So we know how to look back in time, how to measure distance, and how to measure speed. So in 1929, when the worldwide economy collapsed, the astronomical world expanded. This is a modern version of Edwin Hubble's chart. And what he's plotted here is how far away is a galaxy, and we measure here in millions of light years. And on the vertical axis is how fast is it going. And you can see that they're all going away from us. And you can see that the straight line fits the data quite well. It means that the distance and the speed are in proportion. This is exactly what you would get if you had a little fireworks and you let it blow up and you measure the speed of all the particles, and the faster ones would go farther, right? Sounds simple. So you can easily calculate back and you say, well, divide the distance by the speed or the velocity. You get some number which is in units of time, and so that's about how old the universe looks like it is. So this comes out about right. Not quite, but about. And so when this was seen in 1929, the immediate conclusion was the universe seems to be expanding. It's a few billion years old, and this is a great shock. Because before that, there was no hint. People had pretty much assumed that nothing could possibly happen. The universe has always been like this. In fact, for many years after this discovery, it was still the major alternate theory was it only looks like this. And it's not really. So that was called the steady state theory. But in 1929, the economy collapsed and the universe expanded. So some of this was expected, some of it wasn't. Alexander Friedman, a Russian guy in the upper left corner there in 1922, applied Einstein's equations of the universe for gravity, and he calculated that Einstein's theory said the universe should be expanding or contracting. Georges Lemaitre did it separately. He's the guy in the cleric's collar there. He was a Jesuit scholar in Belgium, and he did the same as a mathematician. He calculated the equations for the universe, and he said not only is it expanding or contracting, but in addition, we should think about the origin. He called it the primeval atom. So he was, I think, the first person to give voice to, or give a name to this thing we now call the Big Bang. So he explained this in 1927. Einstein said, that cannot be. You are a very bad physicist. And then 2 years later, Hubble made his discovery, and of course Einstein had to apologize, which he did. Anyway, the other folks here are theorists. George Gamow was from Odessa in the Ukraine, and he was working. This microphone keeps going off. Does it seem that way to you? Okay. Anyway, George Gamow. Yeah. George Gamow was working at George Washington University in Washington, D.C., and he had these young fellers here. Robert Herman was his postdoctoral student, and Ralph Alford was his graduate student. And they were thinking about this Big Bang that had been imagined and discovered. And they said, well, okay, it was really hot, therefore, where's the heat radiation go? They predicted that there should be heat radiation left over from the Big Bang. And they predicted that it would have the temperature of a few degrees above absolute zero, which turned out to be right. So this was in 1948 that they made this calculation. Here are a couple of more modern physicists. Rashid Sunyaev, a former Soviet guy, now circulating worldwide, and Jim Peebles at Princeton, author of what I think is one of the very best textbooks in our subject. Anyway, all of these people have thought a lot about what we should be seeing and pretty much got it right. Now, what have I got next? I wanted to explain that although we have discovered that there is a Big Bang, we have not discovered that there's a center or an edge. And almost everybody that I tell this story to says, well, where's the center? Where's the edge? And the astronomers have not seen one. And we've looked, I tell you. What would you think the center would look like? Well, it would be a spot that's different from all the others in the sky. Or if, say, the universe were spinning, maybe you'd see two opposite places that look like an axis or something. Or maybe if we're not in the middle, you'd see that one side of the sky was darker than the other. Well, none of these things have turned out to be. And so we step back and we say, well, maybe the laws of nature don't require a center or an edge. Maybe the whole universe is infinite and it's just doing this. And the mathematics works out perfectly well, as far as we know, for an infinite universe to be expanding. Now, we don't have a cause for that, but at least the mathematics will describe it. So I've got my three astronomers here. The one on the left draws his Hubble diagram and says, okay, well, the velocity is proportional to the distance. Divide the distance by the speed. The Big Bang was 1 hour ago. Okay. Now imagine what the tortoise astronomer does. He says, okay, well, this distance here is 1 kilometer. The relative speed's 1 kilometer per hour. I look behind me. Okay, I'm in the middle too. There's no grass under these guys so that they know who's moving. So anyway, there's no grass in space either. So astronomers have no way to determine who's in the middle. And the conclusion from that is there's probably not any middle. And that's how the law, Hubble's law, works out that way. So, sorry, we cannot see the center or the edge. There may not be a center or edge, but in any case, if there is one, it's too far away. So, I also can't draw you a picture. Not really. What I would need to do to be able to draw you a picture is to step out into another dimension. And maybe there are more dimensions, there may be 11. But at any rate, we are not able to draw you a picture from inside, because we ourselves were inside this, whatever it was, explosion. I will have maps for you later that show you what it looks like from here. And it does have some features, but you cannot look at it from the outside. Now, astronomers will typically say that the universe was the size of a tennis ball or a golf ball when it was a few fractions of a second old. So I guess the number one question that yields is, well, how can that be? Isn't the universe awful full of stuff? Isn't the universe awfully large to go into that little ball? But the calculations say you could run the universe backwards and it would fit. And this is how it goes. Well, number one, space is almost completely empty. The stars are extremely far apart from each other. And they wouldn't touch until you'd compress them immensely. Then if you got the stars all together and you squeezed in even farther, they would go in farther because atoms are almost empty also. The atomic nuclei are really tiny compared to the size of the whole atom. So squeeze harder and break the atoms apart until the atomic nuclei start to touch, and you've squeezed an awful lot. Now, if you want to squeeze even harder than that, then you can rip the atomic nuclei apart and turn them into quarks, which are flying around loose, but they're even smaller than protons and neutrons. So you can keep on going, and at some point the laws of nature stop applying, at least the ones that we know about. So we don't know what happens if you squeeze even harder than that, but probably the universe was like that. So this is how it could be that the whole universe was in a ball this big, or at least I should say the whole observable to us part of the universe. So Next question is, if this is so, how could it be that this thing is flying apart and has still turned into people? So something had to happen, and what happens is that gravitational forces acting on the primordial material stop the expansion, at least in some places. So the expansion goes out and it slows down in places, and matter starts to pull itself back together again. And then because of the way gravity works, it's able to make stars. Stars can release nuclear energy, and that can support life on Earth. A very abbreviated story. Now here is the calculation that says how this original uniform material could possibly turn itself into galaxies. And this is a box of primordial material moving under the force of gravity. So it might have been like that. We'd like to know, of course. But we have a lot of computers that agree that this is the sort of story that might have happened. And supercomputers are very good at this, and astonishingly enough, the astronomers are pretty much agreed about the forces of nature that they have to put into the computer simulations. So we'll know in some years whether this is right, I think. But we do get a surprise every now and then. It was known for a long time that because gravity is an attractive force, the universe ought to be slowing down. The galaxies are pulling back on each other, therefore slowing down must occur. And a great objective of science was to see how much we're slowing down, because that way we'd be able to deduce how much the gravitational force is and how much stuff is in the universe. So I have to work on Hubble's plot of velocity versus distance and see what it tells us. So people have been doing that, and we have a surprise to show you later. But now I want to summarize the entire history of the universe on one chart. And so we've got a map of the early universe as made by the COBE satellite, which I'll tell you about. What are you laughing at? We have a story about how the Big Bang supposedly made galaxies, how galaxies were made by small things flowing together. And there's the Andromeda Nebula in the lower left corner with two little satellite galaxies. So we think that's how it works. The small things flow together. Now I guess I should explain the horrendous space kablooey. That's the name of the Big Bang that was given by Calvin and Hobbes. And it was not accepted by professional astronomers, but it's just as descriptive. And one thing that actually sort of tells us, which isn't necessarily agreed upon, is that it suggests that it's actually space itself that's having an explosion. The way I've described it, it's just, I sort of talk as though it's the matter which is flying apart. But another way of thinking about it is space itself is flying apart. And so you can't really tell them apart by measurement, but it surely makes a different way of thinking. So at any rate, the horrendous space kablooey, 13.7 billion years ago, now measured very precisely, and in the very first moments, the expansion was extremely rapid. It not only was rapid, it got faster and faster for the first sub-microseconds of time. And then it started to coast and slowed down, and all the initial antimatter that was there in the great explosion disappeared. There's a little bit of ordinary matter left. Anyway, this set up the whole conditions for the expanding universe. When the universe was 3 minutes old, the universe managed to create helium nuclei from protons and neutrons, and then went along for another 389,000 years of getting cooler and cooler until suddenly it became transparent, almost overnight. It took a few thousand years to do this. Suddenly the universe became transparent, and so the heat radiation that existed at that point, we can now map. So that's what that little picture is in the upper left. The pink and blue blobs are a map of the universe as it was when it was 389,000 years old. So then a lot of things happened which have never been observed, but are hypotheses here. The first generations of stars occurred. We think that they would explode. They would produce the atomic nuclei that we need to exist. Then galaxies might form even after that. Now here we have a marker for us. The Earth and the Sun are formed only 4.5 billion years ago, which means that this is only 1/3 of the whole age of the universe. We're new on this universe, just arrived. And then you have to go most of the history of the universe passes before mammals like us turn up. And only in the last 1 or 2 million years are the famous zoo animals and the mammoths and people like us actually walking around. Jump ahead another million years and we get to Galileo. 400 years ago, almost, Galileo perfected the telescope, pointed it up at the sky, and caused a revolution and got himself in jail. But we're going to celebrate this event in 2 years as the International Year of Astronomy, because it's a United Nations sponsored thing. We're very happy that he did that. Then another 300 years passed, and Einstein gave us the special theory of relativity. 1905, it was his, what he called miracle year, and he made 4 very amazingly important contributions to science as a young patent clerk. And there's a wonderful story there, too. At any rate, 49 years ago, NASA was founded. And, of course, we were founded because the Ruskies got there first. We celebrate this month the fact that we've had 50 years of space exploration. And I personally think that it was a good thing for us, this country, that somebody else got there first and gave us a good kick to get us interested and to do the right thing for science and the engineering that it took. And I look around at our very prosperous society, all based on technology, and I think the investment that the country made 50 years ago because of that event is the basis of almost everything that we see now. Or don't see. Okay. So in the next few decades, we may see signs of life on another planet. In the far future, we have a few billion years before the sun burns out. Before that happens, if we get space travel to another star, people will want to go, I think. Around that same time, the Andromeda Nebula, that creature you see there on the left, is going to collide with our own Milky Way, so they say. And it may even be that our sun transfers its allegiance to the other galaxy. And, or maybe that the 2 galaxies will merge. I have a movie of how that could happen. After that, the universe will continue to expand, and apparently it will continue to expand faster and faster, and that's a bit of a surprise. And so future astronomers in 100 billion years will have very little astronomy to do, because nothing will be burning anymore except a few very small stars. So anyway, there's the brief history of the universe, which might be true. Now, jumping ahead to when I was a graduate student, I had been at Berkeley, California for 2 years hunting for a thesis project. The cosmic microwave background radiation had been discovered just 5 years before that by Penzias and Wilson over in New Jersey. So anyway, it was a brand new discovery. Every student and every faculty member in physics was thinking about what should I do about this. And as it happens, the initial measurements included a lot of wrong data. And that was actually very exciting because if there's wrong information out there, it's a challenge. We have to go test that. And so a graduate student should be able to build an apparatus that would see if those wrong data were actually wrong. So, of course, we were starting to do that. And I found Paul Richards and Charles Towns had already struck up a collaboration at Berkeley to do this. And so with Mike Werner, who was a postdoc, I and a fellow graduate student, David Woody, started various projects there. This was ancient times. People still used vacuum tubes for amplifiers, and hardly anybody these days even knows what one is. A lot of mathematics was still pretty elementary. We didn't have a pocket calculator. The fast Fourier transform, which is pretty much a basis for communications technology these days, that didn't exist yet either. And we programmed our computer with paper tape, which made hanging chads. So it's like saying, I guess, astronomers walk to school in the snow barefoot. Well, in 1974, I had had a hard time with my thesis project, and I'd gone off to New York City to get a job at a NASA laboratory to do radio astronomy. But at the same time, just 6 months later, NASA issued an announcement of opportunity calling for new satellite proposals. So this is 5 years after the Apollo landing on the moon. NASA's moving into science at this point more. And they got 150 proposals. roughly, including one from a group that I organized as a young postdoc, 28 years old, and a couple of others that competed with us, and several, well, a great many others. So I didn't expect anything to happen, but we knew the subject was important. And here's what the state of measurement was. This is a temperature of the radiation versus wavelength, or number of waves per centimeter. And this does not look like a straight line. It should be a straight line. It surely did not look like one. And it looked like there was big trouble. So obviously a very important subject. The whole universe is at stake. So in 1976, NASA said, okay, we'll start up a team. They chose 4 members of my team and 2 other people from the other 2 teams. And they started us off building a satellite, or studying one at any rate, at Goddard Space Flight Center. So by 1982, we were approved to build it. 1986, we were pretty far along, and the Space Shuttle Challenger blew up after launch. And after a great deal of soul searching and thought, we found a way. Okay, well, let's see if we can get our satellite to go up on a rocket again, instead of going up on the space shuttle. So 3.5 years later, we actually got it into space. And it was a pretty miraculous project, an engineering tour de force. Bearing in mind that we started this project when engineers used pencils and paper. So this is what we built. Here it is, an artist's concept as it would be in orbit. Let's see, it is in orbit about around the Earth. Earth is down there. Sun is shining in from the side to shine on the solar panels. The spacecraft is spinning around the symmetry axis and looking always away from the Earth. And for the physics students here, I'll say, well, there's a challenge here. How are you going to make a giant gyroscope like that change the pointing direction as it orbits around the Earth so the spin axis always points away from the Earth? You can ask me later. Think about it. At any rate, this is still up there, actually, and it's still spinning, but it's not taking any data. There are 3 instruments up here. There's a tank full of liquid helium up here, which kept 2 of the instruments down to 1.5 degrees above absolute zero, so it would be cold even compared with the primeval heat radiation, and 3 boxes containing microwave receivers to make maps. So there it is in space. So I'm not going to go into details about how this works, but a couple of things I want to point out. This is my thesis project, Grownup, a modern, better version. And what it's supposed to do is to measure how intense is the heat radiation at each different wavelength. So the critically important thing is over here at the top left, a thing we call the movable black calibrator. This is a big chunk of epoxy plastic. It is actually black, and it's our simulator for the Big Bang. It radiates heat and microwave radiation just exactly the way we think the Big Bang should do it. So if you make a measurement of the sky, and then you rotate that pivot and put the calibrator body in place of the sky, and you get the same answer, then you have proved that the Big Bang is the best theory you have. So the rest of this is details, but I do point out that the basic concept of this was invented by Albert Michelson, who was the first American Nobel Prize winner in physics in 1907, almost a century ago. Well, it is a century ago now. So that was the first experiment, and it did produce this chart, which is, as mentioned, drew a standing ovation from the Astronomical Society. And to tell you the truth, I didn't know what they were cheering about because I knew this was the right answer, but they didn't. No one knew that this was the right answer because we had had so many decades, well, long time at any rate, 2 decades of wrong measurements, or at least marginal measurements that said this could not be correct. And we had some very bizarre and elaborate theories of the universe to explain those wrong data. So when this came out, everyone could see that, okay, the Big Bang theory is safe. The whole universe really was a simple thing that Hubble told us about and Georges Lemaitre told us about. And of course, it's a pretty picture. And this kind of curve now appears in astronomy textbooks around the world. One of our team members is an artist, and this is his view of this. The actual number is 2.725 Kelvin. So at any rate, it's very cold. So why was it important? I guess I said this already. The old data were wrong. The old theories explaining the bad data were wrong too. The hot Big Bang theory that we have explains everything. We had something called the steady state theory, which was quite interesting and in a way more interesting than this one. It said actually that the whole universe only looks like it came from a Big Bang. It was actually has been here forever and ever and is being replenished as it expands. And so matter has to be created all the time to fill in the universe. At any rate, this is what it meant to astronomy. And now I want to tell you how we made a map of it. We wanted to see if it was the same brightness in every direction, because that's a pretty important test of whether there's a center or an edge, and also whether the thing is really coming from the Big Bang as people thought. So this is a microwave receiver, block diagram here, and the main point here is there are two antennas that point in different directions. And if you spin this apparatus around and make it orbit around the Earth, you can make up hundreds of millions of measurements that can then stuff them into a computer and make a map. And so making an extremely long and difficult process extremely short. This is the answer that we got. And basically the cosmological answer is here on the bottom. This is what we saw first, and we had to make a couple of changes. What we saw was that the Earth was moving towards the constellation of Leo at a speed of about 300 kilometers a second. And that means that the sky looks brighter in that direction because it's like running into the rain. It looks like it's coming faster at you. But we said, well, we knew we were doing that. That's not what we wanted to know about. And so we subtract that part. Then we get this map. This is, again, a map of the whole sky. And this pink band across here, that's something else we already knew existed. That's the galaxy we live in. There are electrons in our own galaxy. We said, okay, we'll get rid of that part too. And so we did that. And this is the map that we got left over with. And that's a map of the Big Bang itself, as seen from here, as seen from the inside. So this map, when published, drew Stephen Hawking's comment that said that this was the most important discovery of the century, if not of all time. So, okay, Stephen, thank you. To tell you the truth, I didn't really agree with him, but I still agree that it's very important. I thought Einstein's discoveries were a little more important. But nevertheless, this tells us something very important about how we got here. Because this is a map of how the universe was when it was extremely young before any of us were here. And if we could understand these spots, we would know why we are here. And that has now been done in a large degree. There have been thousands of papers published analyzing that pattern of speckles. And we now have a pretty good agreement about what they mean. We also have even more data, better maps now, which I'll come back to. But this I just wanted to show you also, this is the third apparatus on the project was to make a map of the sky at infrared wavelengths. I'm going to skip over what they found, although it's very interesting, because there are many things I want to tell you. So anyway, this is what the Nobel press release said. They were giving us this prize for the discovery of the black body form, and that's the graph with the little boxes on it. That's the black body form. It says that the universe matches that piece of black plastic. And the anisotropy, which is Greek for not the same in every direction. That means the pink and blue blobs of the cosmic microwave background radiation. So it really happened. Here we are. There's the King of Sweden, and he's handing me my diploma. And a little medal about this big, which does not have a string on it. You cannot wear it on your neck. And the money came later. It's now in a foundation, which I have not spent yet, but is for science and the arts. And now a successor project was made. This is the microwave anisotropy probe. It was put together also at Goddard Space Flight Center in partnership with Princeton University. And now you see a lot more speckles. And these are, well, fortunately, number one, they agree with the map we got the first time. So we got it right the first time. But the much more detailed map conveys vastly more statistical information, and it has confirmed a pretty amazing thing, which is that we did not know what we were talking about. If you can't see the caption, it says, "Scientists confirmed today that everything we know about the structure of the universe is wrong. And this is actually the original caption in the New Yorker. I did not have to write it. So what was that we were wrong about? Well, we're not here alone. That's number one. If you add up all the stuff in the universe, 4% of the universe is made out of atoms. And we have only found a small fraction of that. But anyway, we know this is important because here we are, right? We have now interpreted that pattern of speckles to say there's 6 times as much other stuff, which we call dark matter, and it's responsible for almost all of those speckles. And moreover, if it weren't for that dark matter, we would not be here. Because this dark matter, and with all those little speckles, that was the seed material that made galaxies form, and made clusters of galaxies form. If the early universe had been perfectly uniform, no hot and cold spots, we would not exist, because the universe would never have bothered to get around to making galaxies. And so it's very important. We don't know what it is. We know how much of it there is, but we don't know what it is. And we don't know whether we ever will, but many people are optimistic. And so a great deal of effort is being exerted. Then there's something even more bizarre, which we call dark energy, because we know even less about it than we know about this. We can actually make maps of this by various methods. We cannot do that with this, but we are now trying to measure this more precisely and to see if it was always there. So what does that do? This dark energy, what we call this dark energy, is causing the universe to expand faster and faster every day. And so that's the big surprise. We've known about this for about 11 years, I think. So it wasn't discovered with this technique, but it was confirmed. And the pattern of speckles will not match what we see unless there is this collection of 2 kinds of stuff that astronomers can't see either, but we can prove that it exists. So in truth, we don't even know if what we call dark energy is something that exists, or if it's just a defect in Einstein's theory of gravity. But anyway, sometime we may know that. So, many strange things. Now I want to talk about what I'm working on now, which is the new telescope, which we are building at NASA and in a worldwide partnership to study the first things that happened after the Big Bang and many more steps along the way to our own existence. So here I just want to explain about infrared light. Light waves come at wavelengths ranging from very, very long to extremely short, and we call them by different names according to these wavelengths, but they're all the same fundamental phenomenon of magnetic and electric fields going through space in a wave. And here is a sketch that says radio waves come through the air, visible light comes through the air, some kinds of infrared and a little bit of submillimeter waves come through the air, but mostly the atmosphere is opaque at almost all wavelengths, including many infrared wavelengths that would be very interesting if we could see them. So here on Earth we can see with infrared quite well. Here's a person, a match, a cat, and the space shuttle all radiating infrared light. And you can tell how warm something is by how bright it is. Very useful technique. And anyway, technology has definitely improved in the last few years, so we can use this for astronomy. And so we want to build a telescope to use it, and this is what it looks like. And it does not look like any telescope you've ever seen before. So I will sort of outline what the science is and the technology that we have in mind to use. So what is this? This thing that looks like a solar energy collector, this big hexagon of 18 little hexagons, that's a mirror, a big parabolic mirror. It collects starlight or light from distant galaxies, and it focuses it in, bounces it off that mirror and back into the instruments to be analyzed. What you see underneath this structure is made out of 5 big sheets of plastic, and it's about as big as a tennis court, and it is a sunshade. So the way this is in space, the Earth and the Sun are down here, and they shine up towards that, and the telescope itself is in the dark. And that enables the telescope to cool itself off by shining its own heat out into outer space. and so it'll be extremely, extremely cold. That's why we have to put it where we put it, so it can do that. So this telescope is being built by NASA with European and Canadian space agencies. Our prime contractor is Northrop Grumman Space Technologies, which is near LA Airport. And we have instrument packages coming from around the world to do things. It will be operated like the Hubble Space Telescope from the Institute in Baltimore, where we do this now. Let's see. This telescope is huge. It's much bigger than the Hubble Space Telescope, which is, of course, makes it more powerful. But it is so big that it will not even fit in the rocket. And I will show you a drawing of how it has to be folded up. And it is to go up in 2013, which is now just 6 years away, on a rocket which is provided by Europe. So we have to drag our payload down to French Guiana for the launch. And it'll run for at least 5 years. So where does this go? There's the sun, there's the Earth, here's the moon. This is not to scale. And over here, 1 million miles past the Earth, farther from the sun, is a place we call the L2 point. And it moves around the sun all year with the Earth. And then we'll make the new telescope orbit around that spot. So this is a place where we can go where it can cool itself off by radiating heat away to outer space. But unfortunately, it's too far away for us to fix it if it's wrong, so we will get it right. This is how big it is. This is a steel model of it. Here it is on the lawn at Goddard Space Flight Center with a small fraction of the team. This is just the people that work at Goddard with me, about 200 of us here. The whole team is about 10 times as many people as this. It takes a village to produce a telescope like this. And they're spread out around the world. So anyway, a huge project, but well worth the effort. Here's how it folds up inside the rocket. It's very elaborate how it folds up. And so it's a new thing for astronomy to have to fold something up like this. It's not actually a new thing for our company that we're using. There are other government agencies that like to fold things up too. And I do not know anything about it. But the company says that they've unfolded 2,000 things in space and they have all worked. So I think that's pretty good odds. You're wondering what they were. Well, I still don't know what they are. So now I want to show you a little bit of the technology that we had to invent to make this go. None of this was possible 12 years ago. 12 years ago this month I got a phone call from NASA headquarters and it said, we think it's time to start the new telescope to follow the Hubble Space Telescope. We want you to send a proposal tomorrow for how you're going to do it. And I had not been thinking about this, but they said, call up this guy and he'll tell you what I mean. So we did this. And of course, we had to invent all of these new concepts. Everything on here did not exist 12 years ago, but now it does. So we've got 10 major things that had to be invented. Obviously, we had to figure out how to make the mirrors. We had to figure out how to adjust them into place. The Hubble mirror was not right. We learned from that how to make it be right, and we had to adjust it. So that's now an essential part of this project. We adjusted after launch to be the right shape. We had to learn how to hold all the pieces in place. We have 2 new kinds of infrared detectors that both have to be miraculously good, far better than anything we had before. We have even a little amplifier chip that sits next to the detector, right down in the cold to amplify it, and this is not something we've been used to doing. And lots of other things, which I will skip over. But all of these things are now mature, and the review panels have said it's time to go forward, finish the design, and start building. So we're doing that. I'll just illustrate 1 or 2 things here. We have a scale model of the telescope. It's only this big, so it's a little cheaper to work on. And we can now prove that we know how to adjust it. The big problem would be if you couldn't make it work after you built it. So the one way to make sure is practice. We will also test it down in this chamber, vacuum tank in Houston, Texas. This is a historic register chamber. It's so old. It was used by astronauts getting ready to go into space a long, long time ago. Anyway, it shows the telescope down there looking up at the test apparatus. This is one way that we'll go at making sure it works properly before we fly. Now I want to show you some of the science that we're up to. Here are two galaxies colliding in the computer. And there is a picture that we actually took in outer space. So, you know, we actually can simulate real life once in a while. It's not just a cartoon or an artist's concept. They actually said, imagine two galaxies, put them in the computer, put in all the laws of physics that you think apply, and let them collide. So that's what that movie was, a computer simulation of that picture, and for a moment they match. So we're beginning to think that we know how galaxies might be made, but it sure would be a good idea to go get some information, because we can make a lot of wrong pictures too. So with the Hubble Space Telescope, we have taken a picture like this, which is, to an astronomer, absolutely beautiful. And if it were darker and it were the original picture, you would see that there are literally thousands and thousands of little tiny galaxies and some smaller number of very much larger ones that are close by spread out across this picture. And you would say, well, that's lovely, lovely, and there are millions and millions and billions of these things, but how did they get this way? And so the big challenge is, we're like going to a football game, and we see all the customers that have come to watch the football game. And we see the little ones and the grown-ups and the people with coats and the people in baby baskets. And we say, well, how did they get that way? And you have to make a picture. You have to somehow come up with an explanation of how the people got to the football field like that. So we have a little bit of that challenge here. Some of these we think we understand, but we would sure like to see the ones before they started playing football. And so our job is to take an even more beautiful picture that shows galaxies when they were very young. So closer to home, this is one of the most famous pictures we've ever taken with the Hubble Space Telescope. It's called the Eagle Nebula, and it's a part of the constellation of Orion. And it's exciting for astronomers because stars have just been born here. A long time ago, people thought stars all came from the origin of the universe. None of them are new. And then it was figured out that stars some of them only live a very short time. A really massive star will only burn for 3 million years and then it's out. So if you see one of those, you know it's new. So some of these are that massive. They're big, beautiful, bright stars. And this is a place where they have just been made, and maybe some of them are being made right now inside those clouds of dust. So it would be very cool if you could see inside. And so we have taken pictures with infrared light from the ground. And this is showing that you can actually see inside. You can see inside the clouds and see stars that were not there at all in the other picture. Infrared light from the ground shows us is a very rich scientific area. And so you get the same picture, but even much, much, much better in space. And you could learn a little bit more about how stars are made, how planets are made. Here are a few places also in Orion, which were discovered by accident by Hubble. Here is a little cloud of dust with a star right in the middle. It's trying to burn. It's brand new. It's trying to burn its way through the cloud so we can see it. Or maybe not. Maybe that's not why it's doing it. And quite a few others around here. There's a star in there with lighting up its own little dust cloud. So the planets or stars have just been made there. Maybe be very interesting to go look. So we have a movie, artist concept movie, of how our solar system might have been made. What we're showing here are little rocks flying around in orbit around a central star. This is before planets have been assembled out of rocks. And so here they are. It's a lot easier to draw a movie than it is to figure this out in real. But one of these days, we would like to get the data that would tell us if a movie like this is correct. So it could be done. We have lots of good places to look. And we even have places where we could find some planets. Here's a picture that illustrates one such place. This is a place called the star Fomalhaut, or Beta Piscis Australis, I think, in the southern hemisphere. It's a very bright star. And it has been seen with 2 telescopes in space to have a cloud of dust orbiting around it. It's shaped like a ring. And curiously enough, this ring is not centered on the star. but is pulled over to the side. So what would do that? Well, we think that there could be a big planet over here, much bigger and more massive than Jupiter, but we know more or less where it ought to be in order to make that pattern. So we even calculate that our telescope that we are building could see that planet. So there's a chance. There is also a remarkable possibility that we can see a planet go in the front of another star. And this is the moon going in front of the sun, as seen by a NASA observatory called Stereo, which was built just so we could study the sun. It just happened that the moon flew in front of the sun for that trip. And it tells you that there's a lot that you could learn from watching that happen. Once in a while it is possible. Here's an animation of another star with the planet going in front. What you see is a graph that shows the total brightness diminishes when the planet blocks some of the starlight. And so you can tell how big is the planet compared to the star by making that graph. And if you're lucky, you can even tell whether the planet's the same size at every wavelength, which tells you about the chemistry of its atmosphere. And it also could happen that once in a while the planet will go behind the star. And you'll be able to notice that, again, the brightness diminishes. And now you can tell how much light came from the planet itself. So both of these have been already done with our telescopes in space, with the Spitzer infrared telescope and the Hubble Space Telescope. So with this, we can now learn about planets around other stars. And quite a few have been found that do this, although not a very, well, maybe I should say quite a few means a handful. But we have already a list of over 200 planets found by other methods around other stars. So there's a lot to look for. And there are even places here in the solar system which could be alive. Now, I guess a lot of you are pretty aware that we're trying to go to Mars with various robots to hunt for life on Mars. And in fact, one was just launched a few weeks ago. It's going to go dig up the ice in one of the northern polar regions of Mars. It's called the Phoenix mission. Anyway, but that's not the only place to go look see if something's alive. There are 2 satellites of Jupiter that have oceans covered with ice sheets. And this is one of them. It's called Europa. All 4 of these bright planet stars around Jupiter, bright satellites of Jupiter, were discovered by Galileo, actually. So anyway, Europa is one of them. It has an ocean. It's covered with ice. And you can see this thing that looks like an eyeball is actually due to mud or something that's been coming up through the cracks in the ice. So you would think if you could land something here and analyze the mud that came up from underneath, you'd learn something about life that might exist or might have existed in the ocean underneath. So there's a lot to try here. Now, this is an extremely difficult project, but a lot of people would like us to try it. So maybe we will. Coming in the longer-term future, we have at least 3 different ways in mind to go look for planets around other stars and actually see planets like Earth. And what's illustrated here is just one of the 3 methods. This would use infrared light. But the thing that people are really after is to know the chemistry of the atmosphere of such another planet. And if you found 3 chemicals, you would say it's alive. The 3 you would be looking for were carbon dioxide, water, and ozone or oxygen. Because here, at least on Earth, we have oxygen because of photosynthesis. And if we saw oxygen along with these other things, we'd say, oh, that seems a lot like Earth. Maybe that planet's alive. So that's a tremendous hope, and I think within the next few decades we will have the technology to make this measurement one way or the other. So we won't be able to answer all the questions about how we got here from the Big Bang, but we'll have a lot more than we have today. And so that's as much of the story as I can tell you in an hour, but I will be happy to have questions. And thank you very much for coming.